पूरा पके. Now we will weight the sample. पानी ना अच्छी सर कि कष्ट. Total 380 grams of weight sample we have taken. 380, 200, 150 and 10. Now we will put the weight moist sample into the drying column. Now the air is coming out to dry this moist sample, and that is how the dry fluidization braid act. Hot air will pass through it, will flow from downward to upward, drying the materials kept in this. Air is flowing upward direction, in upward direction, and the grains are drying down. Now dry fluidization is taking place by the hot air. is happening rapidly in the fluidized bed. This is the dry fluidized bed. From this we can check it that the sample is dried. पूरा पकड़ अच्छा dry fluidization is taking place by the hot air. Drying is happening rapidly in the fluidized bed. This is the dry fluidized bed. From this we can check it that the sample is dried. Calculating the weights, we can see that 200 grams, 100 gram, 20 gram, 10 gram, 5 gram and 1 gram weight is used. Total weight is 336 gram, which is less than 380. That means our sample is dried properly. Thank you so much.
అంతవరకు వెయిట్ చేయి అంతే ఓకే initially the difference between spouted and fluidized bed makes between the spouted and fluidized bed makes the difference at the distributor itself. If you can see it, the distributor will have number of holes passing to pass the air to the bed, but this is the fluidized bed. When a certain point of diameter is kept at the center, which air could pass through the bed, then it makes the difference of the spout and this is the difference between spouted and the fluidized bed. This is the basic first initially air has to be passed through the bottom of the conical section here, because when the air has passed from narrow end to the wider range, this is what it has designed. From here, a material is fixed here. It is called a fixed bed. Initially, what will happen? Spouted bed has gained tremendous attention in 1950s. In Canada, initially they have used for drying of wheat, drying purpose initially they have started. Now it has many applications in not only in drying, coating applications, especially in pharmaceutical they are applying a lot. Based on this, I have taken a material called cellets. Initially these cellets are used as these are made up of API. Upon this, there are many types of coating purpose. Depending upon that, initially the cellet particles which are made up of microcrystalline cellulose, beads have been taken which are of 100 micron. These are the bed material size we are using today at different bed height. Initially it is in conical section. So when the spout is given here, a fixed amount of bed has been used. This is called fixed bed, spouted fixed bed. When the required amount of velocity has been applied through the bed, then here two types will be classified. One is internal spouting and external spouting. Internal spouting makes the fixed bed, internally the spouting will appear here only. This resembles that the bed expansion will take place from here to here. For example, bed expansion will happen. This everything can be happened inside only. The variation what we can observe is bed expansion only. Once the internal spouting has developed, if we go on increasing the velocity, then we can find out the external velocity, external spouting. So external spouting will be like, this is the packed bed, expansion will be there, and spouting will appear here. Like as we seen many places like spouting, spout like fountain, how it looks. These are three types. One, this spouting is symmetric spouting, asymmetric spouting, and dilute spouting. Symmetric, asymmetric, and dilute. As everyone knows that from axial radiation, this is the symmetric. Asymmetric, from one direction it moves the particle and fall through the other direction. This is called asymmetric. And dilute, the spouting will appear, but all the particles will be distributed whole around the column. That's why this extension part of the cylindrical column we have fixed. Then we can observe the dilute spouting. In dilute also we can see the particles which are clusters, bubbles can be appeared at the bottom of the bed, and it in air pockets will appear, and the particles clusters has been appeared also in this. Everything we can see here clearly. First initially we will pour the bed sample here. Anyone is having any doubt? Shashi, go now. Pause it. Okay. Now this is the fixed bed height. It is 12.5 centimeter. Manometer is required, so that rotameter is required to measure the velocity of the air. It is in RPM, LPM it is, that we have to convert it based on the velocity we have given. And this is the manometer. With this manometer we can identify initially the internal spouting will happen. So, when the internal spouting will happen, velocity versus pressure drop, if we draw a graph between these two, in internal spouting linear graph can be observed. Means if we increase the velocity, pressure will also increase simultaneously. Once external spouting will happen, then the pressure drop will fall and maintain constant pressure. For this purpose we have all this rotameter and manometer we have been fixed, and the bed material we have used are cellets, which is 1000 microns. So that can we start the experiment. And we have given 120 LPM. Then we can see that of bed expansion has not been there, and the pressure drop. Here the bed expansion has happened, then the spouting is appearing. This is called the external spouting. Spouting will appear. Why? Because the velocity is not in the one direction. Velocity of the air is not in the one direction. When we increase the velocity, spouting has been increasing. Spout has been increasing. And it is like the particles which are spouting, which have gone through the space, then it is like counter current flow has been, the particles are moving down. This can be observed here. Shall I? Been appearing, only the particle movement have been there. When the velocity has been increased, this is the C 100 LPM. Then the external velocity has और ज़्यादा air. See this spouting. Velocity और ज़्यादा sir. Explain this. I will explain this point. Sir, close. Drop we will get is high. Delta P is high based on differences between the manometer we have connected. One is H1 and H2. The difference between this is H, and pressure drop delta P equals to rho CH. Using this formula, we will calculate the pressure drop. Initially, when the particles are packed like this, the required amount is, if not sufficient, the air will flow, the velocity of the air will percolate through this, and it passes through the packed bed. Then there is no movement of the particles takes place. That is at static condition only, but pressure will be measured here is pressure drop will be high. When internal spouting will happen, the pressure drop decreases. Why? Because the particles, it lifts the particles up. Here the drag acts high because the velocity is as compared to this velocity lifts, the particles will suspend or the particles will move. This will appear because we are adding the spout at the center point. The spout will appear, then the velocity will reduces. Here when we go on increasing the velocity, what is happening means the particles which are getting agglomerated. This is because the clusters have sir and ma'am have discussed earlier that all these particles, air will flow like pockets, and the particles will get aggregated here. Once it reaches its means gravity when it is low, when it is high, the particles will fall down. Because of agglomeration, the density will increases. When agglomeration happens, the density of the particles all together will be high and the particles will fall down. Any questions? Like you can see this pressure variation. Okay. Can be takes place here. When increasing, particles are increasing high. Spout has appeared, and that difference has been very less. We can see this. All the particles. This is the air pockets, and this is the clusters. We can appeared here. And this asymmetric spouting, because spouting is happening from one end and the particles are falling from the other end. You can observe this direction. Almost the particles all are in suspended stage. This stage is called the diluted spouting. Getting the maximum height it has reached. The height direction of the particles. When spouting is happening, the velocity particles are forming like this, and this is the velocity of air with respect to spouting. This is the particles are traveling along with the air in upward direction. That it means like co-current spouting. When it reaches the maximum, when ut is high, then velocity particles are falling back, and particles are moving in counter current. It is opposite to the velocity of the air. As I already told, asymmetric spouting. Asymmetric spouting means the velocity of the particles, these are moving like this and falling in opposite direction. It is not appearing at the center of the axis. If the spouting is appearing here, means particles are moving in this direction and falling in this direction. It is called symmetric. This is asymmetric. Are coming in this entrainment. These particles are coming down, which is called counter current particles. Counter current flow is happening here. They can ask me. No doubts?
Solid and gas solid. Hydrodynamics of the gas solid system and liquid solid systems. Here hydrodynamics means how the bed behaves, that includes the determination of the minimum fluidization velocity, pressure drop, and bed expansion, how much it is expanding during the fluidization process. So first I will show the hydrodynamics of the gas solid system, then we will show the hydrodynamics of the liquid solid systems. And here you can see this is the rotameter. From this side you can show this. We will see that how the bed height is changing, that is bed materials getting expanded and bed height, total expanded bed height. Then from the expanded bed height we can calculate bed expansion ratio and the bed fluctuation ratio. And similar, here the bed expansion ratio is the expanded height divided by the static bed height. Now bed fluctuation will be the expanded height, it fluctuates within some minimum and maximum value, that is minimum expanded height, maximum expanded height. We can take average of that, which will be the average expanded height to static bed height is the bed fluctuation ratio. So from the pressure drop versus velocity plot we can get the minimum fluidization velocity. Now here just I will show that how the bed is getting expanded. Then with the repetition of that experiment, that is by varying the flow rate, we can get various pressure drop, and manometer is here in between. Here it is manometer is shown, and from here we can get the differential height. So multiplying with the density of the liquid, that is fluid, which is taken in the manometer, we can calculate the pressure drop. Now after getting number of readings of the pressure drop against the velocity, we can plot that delta P versus velocity. From that we can get the minimum fluidization velocity. And fluidization occurs just after the minimum fluidization, that is in the minimum fluidization all the materials are ready to move up and down. Because in the static condition, when there is no supply of the air, the bed behaves like a packed bed, and with increase in the velocity of the superficial velocity of the fluid, the void among the particles get expanded, and gradually with further increase of the velocity of the air, the bed materials are free to move. And this we can see now here the rotameter, just from this side you can show. First we can see here the rotameter reading is 0. You can see that now the bed is static, it is not getting expanded, and pressure drop also it is almost same. There is no slight because completely 0 is not maintained, so that it is almost same, no pressure drop. You can see here by increasing the flow rate, now we increase to 5 liter per minute. Still it is not expanded because initially the air fills the voids among the solid particles. Now with further increase in the flow rate, we can see some particles here in the bed. You can see some particles are getting movable or getting expanded from its original position. It is the entire bed is not expanded, and with further increase in the flow rate, now you can see I made it 10 liter per minute flow rate. Now with this you can see the entire bed material are getting expanded or movable. So here we can see that this is the height up to which the bed is getting expanded, that is roughly it is 18 centimeter, and that means expanded bed height is the 18 centimeter. It is coming up to 18 centimeter. And if you say that what is the minimum, this is coming maximum bed height up to 18 centimeter. The minimum expanded height you can see it is coming 16, whereas static was, just 1 second I can show you the static bed height. It is nearly 15, means 14.5. So minimum with the 10 liter per minute you can see, and with this the maximum expanded height, you can show here it is coming around, now it is more than 18 it is coming, so it is about 19, and minimum is coming about 16. So thus average of this, if you take 19 plus 16 divided by 2, that is the average expanded height. That divided by 14.5 will give you the fluctuation ratio, and 19 divided by your 14.5 will give you the expansion ratio. So then with this 10 liter per minute flow rate, we can see that here the manometer, it is on this side, it is, you can see here, and on this side up to here. That means delta H is coming around you can see around 4 it is coming. So delta H multiplied, here it is potassium permanganate is taken as the manometric fluid, and any fluid whose density is more than the density of the fluidizing medium can be taken in the manometer for measuring the pressure drop. Here we will get the delta H, differential height in the two limbs, multiplied with the density of the manometric fluid will give you the pressure drop. So this is about the hydrodynamics of the gas solid fluidized bed. Now we will move to the liquid solid fluidized bed.
Now the participants, I am going to demonstrate the characterization of a liquid solid fluidized bed. A very simple setup available in the laboratory that I am going to show you. Liquid solid fluidized bed, liquid is stored in a tank. As you see, that liquid is there in this tank, and this liquid is pumped by means of a pump here at the bottom, and this liquid flows in the upward direction, and this is the fluidized bed. This portion is the fluidized bed. In the fluidized bed, particles are there, and this is a batch liquid solid fluidized bed, where solid particles are already dumped in this bed, and the height without the flow of the liquid, it is the static bed height here. So when I will allow the flow of the liquid through this bed, and liquid will flow through one distributor plate, it will enter to the vessel, and the liquid will rise, and finally liquid will come out, and recirculation of the liquid is there in this system. The pressure drop for this can be measured using manometer. Already other experiments you have learnt how to measure the pressure drop using the manometer. So only I want to show you that earlier you have seen that gas solid fluidized bed, which is called as the heterogeneous fluidization. Gas solid fluidization is heterogeneous fluidization, where gas bubbles are formed, and depending upon the velocity of the gas, smaller bubbles are there. As you increase the gas velocity, bigger bubbles are formed, and finally you reach at the slug flow regime. And in the form of a cloud, the solid particles move with the bubbles of the gas, which is not in the case of liquid solid fluidization. Liquid solid fluidization is called the particulate fluidization, smooth fluidization, or homogeneous fluidization, where uniform distribution of the particles are seen. In gas solid fluidization, heterogeneous, the bed is heterogeneous because large bubbles are there, smaller or larger bubbles are there. But in liquid solid, the liquid is well distributed, particles are well distributed, uniform fluidization will get. And as we increase the liquid velocity through the bed, after the beyond the minimum fluidization, first there will be no change in the height of the bed up to the liquid velocity reach the minimum fluidization velocity, and beyond the minimum fluidization velocity, if we further increase the liquid velocity, then expansion in the bed will be there. That I am going to show you. So the liquid, which is water here, stored in the tank, and that is getting pumped by means of a pump, and there is a bypass line. Now the bypass line is fully open, so that there is no flow of the water through this bed. Now if I close this bypass line little, so then flow will be there through the bed. Now you see that liquid level is increasing. That means liquid is entering to this bed. But as the liquid is entering, moving in upward direction, but there is no motion of the particles. Particles are not moving. If I further increase the liquid flow rate by closing the bypass line, liquid velocity will increase gradually. Liquid velocity is increasing. There, bed is not getting disturbed. Some dust particles are there. Okay, those are just in the form of agitation over the bed is there, but the glass-bead solid particles, they are not moving. So if I gradually increase this, the liquid velocity by closing the bypass line, by reducing the bypass flow, now the minimum fluidization has not reached. So gradually I am increasing the flow of the liquid through the bed. So as the flow of the liquidity through the bed is increasing, the liquid velocity is nothing but the flow rate divided by the cross-sectional area of the bed, that is the superficial liquid velocity. So the superficial liquid velocity is also increasing. And as the liquid velocity is increasing, you know whether the flow of the fluid either in the Stokes law regime or it is in the Newton's law regime. Depending upon the flow regime, either it depends upon the first power of the velocity or the second power of the velocity. That means with increase in the fluid velocity, the drag force that the liquid exert on the solid particles will increase, whether linearly it will increase or it will increase with the square of the velocity. That depends upon the flow regime. But it is a low flow rate, so it is a laminar flow kind of thing, and in this laminar flow, low flow rate, it will depend upon the fast power of the velocity. Still that liquid flow is there. Now you see the other line, liquid is coming, the water is coming, but this flow what is happening through the bed is not sufficient to make the bed fluidized. Now the bed is just getting fluidized. Now you see that bed started moving, little bit the height increase is there. So minimum fluidization is reached. If I further increase the liquid velocity here, then bed expansion will be there. And you see little more. If I further increase the liquid velocity, the bed height is increasing. With the increase in the liquid velocity, I am increasing the liquid velocity. You see the proper fluidization is there, and here you see that uniform distribution of the solids are there, no bubbles are there. It is the liquid solid fluidized bed. Okay. Smooth fluidization or particulate fluidization is there. If I further increase the liquid velocity, this is the way the bed height is increasing. Gradually the bed height is increasing. So you are getting a smooth fluidization here. So the difference between gas solid fluidization and liquid solid fluidization you can see. Now I will make this a three-phase fluidization by allowing the gas bubbles. As you see here, this water storage tank is a shallow water storage tank, and as per the capacity of the pump, and because of the recirculation of the water here, you see that the bubbles are forming here, and those bubbles which are forming because of the vortex of the liquid here, that means the entrapment of the air to the water. So those bubbles are carried out by the pump, and those bubbles sometimes it is coming in the bed. Initially at low flow rate it was not there. Now you can see some of the bubbles are moving. Okay, so this air bubbles are moving, but if I will decrease the if I will decrease the water, have to come in. Air bubbles will be withdrawn by the pump, and that will enter into the fluidized bed. Of air bubbles are flowing. It is a kind of three-phase fluidization you are reaching almost. But it is the air is not, we are not supplying any extra air through any sparger to the bed. But this is because of the entrapment of the air to the liquid, and which is carried out by the pump to the bed, which is coming. So this is the liquid solid fluidization that has the difference over the gas solid fluidization. Thank you all.